This is problem 546, and this is a problem where three books are stacked on top of each other here, and each book has the same length, and the length of one book is given by A, and each has a weight of W, so they're all equal in weight. And what we're looking for is the maximum distance D. So how far can we extend this top book out without the thing toppling over? Okay, so that's what we're looking for here. And I think the tricky part of this problem is figuring out when it actually falls over or topples. All right, so I have a diagram here, and each one of these books has a weight to it, and we can think of that weight just acting along the center of gravity here. So the top book has a center of gravity right in the middle there. So how far could we push this top book out without it toppling over? Well, it actually happens to be as soon as that center of gravity extends beyond the book supporting it underneath, it's going to topple over. So this center of gravity here with the weight W is going to be right along that edge there. Okay, so that's where that's located. And the distance from the second book to the edge here, right, that's half the length of the book, which we then know because the book length is A, that's A divided by 2, 1/2 A. Right, so that's 1/2 A. Okay, now likewise, since this extends halfway up, we know that the center of gravity here of the second book, the middle book, is actually located right at the edge of the top book, right? So that center of gravity here with the weight of W is acting down right along that edge. All right. The question comes, how far can we push this middle book to the right before it topples over? Well, since if it's still standing, we know the thing is in equilibrium. And let's just call this point B. So the point where the bottom book edge meets the middle book, we'll just call that B right there, this point here. All right, and we know the length of the top book is A. So we know that full dimension there is A. Okay. All right. So if this is an equilibrium, we can take the sum of the moments around B, and those should be equal to 0. And we'll call our counterclockwise moment as positive here. So let's take the moments around B. All right, let's start with this middle book W. All right, so the middle book W is going to create a counterclockwise moment, which should be positive. So we have W times the distance that it's acting away. And what is the distance that W is acting away from B? Well, if it's right on the edge here, we know that distance is A, and we know the distance from the bottom book to the front edge of the top book is D. So this distance here should be A minus D. All right, so that small distance here is A minus D. So A minus D. And then we need to do the moments around B for this force here, the W of the top book. And that's going to create a clockwise motion, so around B, which will be a negative moment. So negative W, and the distance it's acting away from B there, what is that distance? Well, that distance is nothing more than D minus A over 2. All right, that small distance there is this total distance D minus A over 2. So we have D minus A over 2, and that is equal to 0, right? The bottom book really doesn't have any influence about the moments around B here, so we don't need to worry about the bottom book so much. All right, so now we need to solve for D because that's what we're looking for. So I'm going to move this over to the other side, So we have on one side W times A minus D, which is equal to W D minus A over 2. Okay. Now the W's appear on both sides. We can cancel those off. And we just have A minus D is equal to D minus A over 2. All right, so I'm going to move the D's over to one side and bring all the A's over to the other. Okay, so I think on this side we should have 3A over 2 is equal to 2D. Divide both sides by 2, and we get D is equal to 3/4 A. Okay, so the maximum distance that we can overhang this top book is 3/4 A, or 3/4 the length of a book. Right? And that is our answer for problem 546.